Kia ora Year 12, welcome to day 4 of the Term 1 holiday trig revision. Actually it's day 5, but the iPad battery went very flat yesterday, so there'll be 2 revision videos today. So the first question here is a really nice scholarship question from way back in 1973, and then the next 2 are also from the Red, Seeley and Agnew maths book. The second one is an exact values one, so don't just grab your calculator to show me tan of pi on 12. And the last one is a general solutions question, but 2 little things that are different in it. You'll notice that here we've got 2 trig functions, so that's a bit funny, and we're going to do general solutions in degrees. Okay, so here's question 1. It's not that bad once you get used to what you've got to do with the square roots. So on the left hand side, this is what I've got. I'm going to move the root 2 cos theta to the right hand side by adding it to both sides. Next thing I'm going to do is to square both sides. So that will give me sine 2 theta plus cos theta minus sine theta is equal to 2 cos squared theta. Now I'm looking at that and I'm not liking it, but I think I can see some kind of quadratic with mixed up cosines and sines in it. So let's get everything to one side. So I'll leave the 2 cos squared theta where it is and subtract the left hand side from both sides. So I'm going to subtract this from both sides. And that's what I end up with here. Now just check that we haven't mucked up any signs. Yep, that looks good. Now the next thing I notice is that I've got cos of theta, sine of theta, but here I've got sine of 2 theta. And I'm still not seeing any common factors or anything nice, so I'm going to just try expanding sine of 2 theta. 2 cos squared theta minus 2 sine theta cos theta minus cos theta plus sine theta equals 0. Now I'd like to be able to factorise that, but it's not hitting me over the head how to do it. So what I'm going to try when this happens is 2-stage factorisation from back in year 10 or 11. So I'm going to look at this pair of terms here and see that I've got a common factor of 2 cos theta. So take that out. It's cos theta minus sine theta. Now I should be feeling really happy because I can see that I've got that factor repeated over here. So cos theta minus sine theta equals 0. Factorising as usual, we get 2 cos theta minus 1 times cos theta minus sine theta is equal to 0. So either 2 cos theta equals 1 or cos theta equals sine theta. Right, so either this factor is 0 or this factor is 0. So working with those, we've got cos of theta is equal to 1/2, and here we've got 1 equals tan theta. And from the first slide, remember that we're just looking for solutions between negative pi on 2 and pi on 2. So that makes it very straightforward. We can just use our graph to think about it. So here's my cosine graph. Just in that part, I'm going to have 2 solutions. And sketching in, really cramped here, sorry about that. Here's my special triangle. So we know that the theta, whose cosine is 1/2, is equal to pi on 3. So this is that first solution there, pi on 3, and negative pi on 3 will also work. And for 1 equals tan theta, just think about your tan graph. You're just interested in the graph between negative pi on 2 and pi on 2, so we've just got one solution there, so theta is equal to pi on 4. So there we go. They're my 3 solutions to that equation. On to question 2. Right, this is an exact values one. We want to show that tan of pi on 12 is equal to 2 minus root 3. So just before we get underway, let's just draw in an angle of pi on 12 here. So we're in that first quadrant, and we want to show that tan of pi on 12 is equal to this. Pi on 12 is somehow related to pi on 6. So let's start with the double angle formula and see where we get to. So tan of 2 theta is equal to 2 tan theta over 1 minus tan squared theta. So we can write the following: tan of 2 times pi on 12 is equal to 2 tan pi on 12 over 1 minus tan squared of pi on 12. But we know that tan of pi on 6 is equal to 1 over root 3. So just to make this easier, let's let tan of pi on 12 equal x. So what have I got now? Well, I've got tan of pi on 6, so 1 on root 3 is equal to 2x times 1 minus x squared. Now, we've got a quadratic here that we want to solve. We're going to have 1 minus x squared is equal to 2 root 3x. X squared plus 2 root 3x. I'm looking ahead and thinking I'm going to do completing the square on it, but in case we're not seeing that, we'll just write it as a quadratic equaling 0. So we have x squared plus 2 root 3x minus 1 is 0. You could use the quadratic formula as well, but when I've got something with a 2 in here, I prefer to go straight to completing the square. So we have x plus root 3 squared. I've added in 3, so I'm going to take 3 out. Minus 3 minus 1 equals 0. And we get x plus root 3 squared is equal to 4. So I'm going to use a new slide to finish this off, because we need to be a little bit careful here, because we're going to get 2 solutions, and we know that there's only one value for tan of pi on 12. So I'll keep going on the next page. Right, so where are we up to? Well, we've got x plus root 3 squared is equal to 4. Taking square roots of both sides, we have x plus root 3 is equal to plus or minus 2. So x is equal to negative root 3 plus 2, or x is equal to negative root 3 minus 2. So this is 2 minus root 3, and that's the one that we need. But we just have to look at this other solution and reject it. Well, x, negative root 3 minus 2 is less than 0, so we reject this as a solution, because we know that tan of pi on 12, which is what x is, must be positive. Okay, so there's that one done. Right, last question coming up. Okay, we're asked to find the general solution to the sine of 3x is equal to cos of 2x. How strange. Well, and we're going to do it in degrees, but that's easy. First thing I'm going to do here is I'm going to use what we know about switching between cosine and sine. So sine of 3x is equal to sine of 90 degrees minus 2x. Or, doing it the other way around, so that will work, I could do this. Cosine of 90 degrees minus 3x is equal to cosine of 2x. So you can choose which way to proceed. I'm going to use the cosine one just because I have a slight preference for getting you guys practicing general solutions on cosine, because I feel like we always do sine. So what do I do when I'm doing general solutions? Well, the first thing I do is I get my principal solution, and it's alpha. And alpha is always the inverse trig function on this thing here. So we're going to do exactly the same thing here. So it's cos inverse of cos of 2x, which is just 2x. Right? So my principal value is 2x. And now, this is my general solution steps. I've got 90 degrees minus 3x is equal to, well, it's not going to be 2n pi, it's going to be 360 n degrees, plus or minus my principal value. Okay, so all I have to do now is very carefully work with two cases. I'm going to have this one, 90 degrees minus 3x equals 360 n degrees plus 2x, and I'm going to have my second case. So each of these will generate a set of values, and now we're just finding a way to write them out systematically. So minus 2x here. Right, so we're looking to end up with x equals blah blah. So here we have negative 5x equals negative 90 degrees plus 360 n degrees. Dividing everything through by negative 5, I get x is equal to 18 degrees minus 72 n degrees. And remember that n is any integer value there. So that's my first set of solutions. I'm going to do the same thing with the other case. So I'm going to add 2x onto both sides, and I'm going to subtract 90 degrees from both sides. So we get negative x is equal to negative 90 degrees plus 360 n, which gives me, dividing through by negative 1, x is equal to 90 degrees plus 360 n degrees. And again, n is any integer. So what I could do now to generate the solutions is I'll just start at probably, say, n equals negative 3 and work my way up with both of those cases up to about, I don't know, n equals 2 or 3. This video is long enough, but what I'd like to do in class is to show you using GeoGebra what's going on here. So you can think about, I'll do it really roughly here, what's sine of 3x? Well, sine of 3x is a squished in sine function, right? It's going to have a period of 120 degrees instead of 360. So that's one cycle there. And then cosine of 2x is a squished in cosine function with a period of 180 instead of 360. So we're looking for those crossover points. So the cosine one is going to go like this. Let's try and draw it roughly. There, it's a really bad graph. So we're looking for all of the points where the black and the red line intersect, and that's what our general solutions down here are going to produce for us. Alright, thanks for watching. The video for day 5 will be up later on today, now that I've charged the iPad.